Hello, good morning. Sorry, I was trying to get the kids off for school. Well, not for school, but off to my friend's house. Give me just a second. I am going to set up your PowerPoint. Give me just a second. All right, and what we're going to do is let me share my screen with you guys. All right, where we left off on on from Monday was we're going to get into all of the drug control laws from chapter number 12. Um, so with that, one of the things that we have to look at is we have these laws and we have drug control laws. And with the drug control laws, we have federal law. Um, and we have this classification of different drugs. Now, there are different schedules for the classification of these laws. So the potential for abuse, physical and psychological dependence, medical value. So this is what the law established, these five classifications. And so it's based on these three things. Now, you have schedules of classifications too when it comes to these different drugs. So you can have Schedule 1, which deals with a high potential for abuse and have no medical use. Uh, so, uh, marijuana was on this list. It's still on there federally, but there's a lot of states now that's saying there's medical use for marijuana. So a lot of states are starting to push towards that now. So technically, marijuana is still a Schedule 1 drug, although a lot of states is pushing for it to be legalized. And I know Alabama is one of the states where it is not legal, but they are trying to make sure that it's going to be legal for medical use. So even though at the state level it may be okay, but federal level it may not be. Now you got your Schedule 2 drugs. They have a high potential for abuse. They have medical use. Um, Severe restrictions. Cocaine actually is on that list. PCP, amphetamines, and barbiturate prescriptions. So those are on there. You got Schedule 3 drugs that has less potential, but is currently accepted for medical use. Barbiturate prescriptions, not covered under Schedule 2. Um, Codeines, and some steroids. So you got some that are on that list that is good for medical use, but at the same token of time, um, a lot of times they don't. They can still be used and abused. Now, Schedule 4 drugs have low potential, so they got different ones. You got Darvon, uh, phenobarbital, tranquilizers, Valium, and all of those, but there are people that still abuse those too. So it doesn't matter which type it is or what schedule it is, it can still be abused. Now, Schedule 5 drugs have low abuse and potential to have medical use. Now, opiate drug mixtures that contain non-narcotic medical ingredients can be that, and so we see that a lot. Now, how do we collect and collect drugs? What happens in these cases? The field investigator has the responsibility that the drugs are properly labeled and they are properly they're properly labeled and everything for um, transportation and getting it ready for the laboratory to be tested. Uh, you want to make sure that you don't get any type of cross contamination. So they try to make sure that it's properly packaged. So you got to make sure that when you're collecting the evidence, that it's collected correctly. Now, most of the time, just as long as you have it in the original container, those tend to be okay. So as long as you got it in the original container, you're fine. All packages must be marked with the information on there to ensure the identification by the officer, and then you got to establish that chain of custody. Now, there's other identification. Now, the challenge is comes in selecting different type of analytical procedures that will ensure a specific identification of the drug. So what you're saying here, Dr. Jones, you basically have to make sure that you have to ID what type of drug it is, because all white powders are really different. It can be different things. So how can you tell whether it's cocaine, uh, uh, baking soda, or some other type of powdered drugs? Could even be anthrax. So you never know what type of drug it could really be. So they have to test to make sure they know what it is. So that's one of the things they have to do. Now, the plan or this scheme of analysis is divided into two phases. So the first phase is you got to screen test what is non-specific and preliminary in nature to reduce the possibilities to a manageable number. And then confirmation test is a single test that specifically identifies the substance. So you have to do all of that. Now, the other thing that you have to do is you got to do your preliminary analysis. So with preliminary analysis, you got to be able to employ a screening test and then making sure that it goes to a manageable number. Now, there are different tests that they have to do. You got to do a series of color tests that produce characteristic colors for more common encounter illicit drugs. So they do the Marquise test that deals with heroin and amphetamines. Then they do the Duquesnoy-Levine test, and that one is for marijuana. The Scott test is for cocaine. The Dilly Copiaille is for barbiturates, and then the Van Erck is for LSD. So there are different types of tests for different types of drugs. So those have to be done in order to see what type of drug it is. And so this is all preliminary. And then you can also do these microcrystalline tests to identify specific drug substances by studying the size and the shape of crystals that form during the drugs mix when you mix it. Because what they have to do is, in order to get those colors, like I said, they can all be like white powders, but in order to get specific colors, they have to mix them in order to see which color that particular powder or whatever come out to be. Now there's other tests like running it on different machines like IR or uh, mass spectrometry and all of that to test for different things as well. So you can, and then it can come back and show that a particular drug or something may be in somebody's system or anything like that. But they do have to do those particular types of tests. Now, when they are at the stage to where they can do conformational determination, um, they do that. Now you have what we call forensic chemists. They will employ a specific test to identify a drug substance to the exclusion of all other known chemical substances. So that's where they go in and do all these other ones. Typically, that's what I was talking about. You're going to use infrared, IR, gas chromatograph, mass spectrometry is used to identify the drug. That's where you come to confirm everything. So they have to do all these different color tests first. Then they go and corroborate that with the different types of instrumentation to actually see what it is. So one thing that even as a chemist myself, we look at quantitative versus qualitative. So um, what it is one just identify the material itself, whereas the latter requires a determination of percent composition. So quantitatively, you have to look at what is the percent composition of this material, and then qualitative looks at what type of material this is. And so even as a chemist, even as a engineer, even going that far because I have an engineering degree as well, we have to look at both. And that's what the forensic chemists do. They have to look at both. So they look at chromatography. And chromatography is just a means of separating and identifying the components in a particular mixture. The theory of chromatography is based on the observation that chemical substances has a tendency to particularly escape into the surrounding environment when dissolved in a liquid or absorbed onto a solid surface. So you can go either which way with that. And I have my students, even when we're in the lab, do like paper chromatography. So that's something that they can do. Now, with that, we have one of the things that we talk about a lot in chemistry, which is Henry's law. And that's when a volatile chemical is dissolved in the liquid phase and brought to equilibrium with an air phase, and it's at a fixed ratio. Now, what it is that with Henry's law, um, what has to happen is it's concentration in liquid, and then the ratio remains constant. Now, with Henry's law, we have to deal with uh, temperature. And that's very important because sometimes you never know. Depending on the reagent, at certain temperatures, those reagents can go away. They can evaporate all of that. For example, alcohol. Alcohols can't get above 70, 80 degrees because they can evaporate. So that's one of the things that we will look at. So with chromatography, what we have is one phase is always made to move in one direction over the stationary phase or a fixed phase. Now, those material has a preference for moving the phase will slowly pull ahead and separate from those, um, and they prefer to remain in stationary phase when they do that. Now, this whole process, now here is just an illustration. The molecules, if you can see them, they are in blue. And so you see some blue there. And then what happens is, um, from the standpoint of me being a chemist and doing chromatography, what happens is you have small particles, you have big particles, you have medium-sized particles. And they can go over a stationary phase, whether it's liquid or solid. Now, those particles will move. Now you got particles that are lighter than some particles. They'll move faster than bigger particles. It's just like if you have them flowing over water and everything. Excuse me. So what happens is they are pushed along faster by moving air. Now these things, two sets of molecules, they're gonna separate from each other, and that completes the process. So let's just say you put a chemical into there, and you put a chemical in there, and then you got liquid phase, and then you got the air phase, and the air phase is just causing them to move. And then what it is, whichever particles are lighter are going to move faster, whichever particles are larger are going to move slower. That's basically what it is. Now, in gas chromatography, the actually gas is called a gas carrier that flows through a column. Now, the stationary phase is a thin film of liquid. After a mixture had traversed the length of the column, it was merged, separated into its components. That's what happens. Now, what happens is it's going to come out on a printout, and that printout is called a chromatograph or chromatogram. And the time required for that component to emerge from the column, we call that retention time. So how long does it stay in there? So that's retention time. So that's what we call that. And so that's what it is. Carrier gas is the gas that moves it along. Now, this is the basic setup of the gas chromatograph. So, and what happened is you got a carrier gas. Usually, this carrier gas would be argon, uh, krypton, a gas that won't react with the particles. So you want an inert gas. So that's your carrier gas. And what happens is it's hooked. Then what you do is you take the sample and you inject the sample in. Usually you use like a syringe or a little pump, and it goes into it, and then you have the column. And in the column is contained around an oven. So when it goes through there, it'll go through a detector, and then the data is recorded. And when the data is recorded, then it goes out as a chromatogram. Now here, what you're looking at is um, a mixture of barbiturates, and is identified by comparing its retention time to a known mixture. And so what they did was they looked at, they know where the, I don't know, I think there's phenobarbital and succobarbital that is on there. And then what happened is, um, that happens, and then what they're trying to say is, okay, this is a these are these two unknown mixture, and what they were able to do is, the last one at the bottom, they ran, you know what butybarbital is, amobarbital, phenobarbital, secobarbital, and phenobarbital. And then you look at the peaks as where they are originating, and you can know pretty much where it is. So these two peaks match up to the phenobarbital and the secobarbital. So that's what they do. What you do is you have to run those chromatograms of everything else first. Then once you run those chromatograms, then you do that. So that's what's going on, and that's what actually happens. Now, you can have thin layer chromatography, and that's TLC. And TLC uses a stationary phase coated onto a glass plate in a mobile liquid phase. Now, this is what I do in the lab at school. So we do a lot of paper chromatography, and we do thin layer chromatography. Now, the liquid will slowly rise up the plate by capillary action, causing the sample to become distributed between the stationary phase and the moving liquid phase. So this is what I use in the lab, and we have machines, very small handheld ones that actually do this. So my students that are in the organic class that comes usually after you guys' class, they're the one, they do a lot of thin layer chromatography in their class. And then my earlier chemistry classes, like my beginning chemistry classes, they do paper chromatography. But by the time you get up, you do some of the other chromatography when you get in the later chemistry classes. Now, because most compounds are colorless, the materials must be visualized by placing plates under ultraviolet light or spraying the plate with a chemical reagent. And so that's what they do. We have the TLC plates in the lab. And what we do is, I don't think I have any at home. And I started to bring one of those machines home with me, but I didn't. But what you do is with it, they put their plates on top of the machines, and then that reads the ultraviolet light. So they have ultraviolet light um, machines that we put them on, and then we put the reagent over it so you can see it. Now, the distance that the spot travels up the thin layer plate can be assigned a numerical value known as the RF value. And this is what it is. So you got your spot, you put on the sample, that little spot there, that little tube, we call that a capillary tube, that's what they use. It's a thin coating of silica gel or aluminum oxide. Our plates at school have aluminum oxide on them. I do have a few that also have the silica gel, but we use aluminum oxide. And then the rising solvent, the original spot has separated into several spots. That's what happened. So that's what you do. This is exactly what we do in the lab. Uh, and I think they got this going on the PowerPoint. That's spectrophotometry. So spectrophotometry is an analytical tool. It measures the quantity of radiation that a particular material absorbs as a function of wavelength and frequency. Now, I have a UV vis spectrometer that is in our lab. We have one of those, and we actually use that to measure different things. So that's one of the things we have. Now, it measures and records the absorption of spectrum of a chemical substance. So we have some small tabletop ones that are in the lab that we use in chemistry. So you see those a lot. Now, what does it have in there? It has a radiation source. It has a monochromator for, or basically something that selects the frequency. It has a sample holder. It has a detector that converts the electromagnetic radiation into an electrical signal, and then the recorder produces a record of that signal. So that is what happens with that. Now, absorption spectrum can be done in visual, visible, ultraviolet, or infrared regions. So I have an IR spectrometer in the lab, and I also have a UV vis one. So those are the main two that I have in the lab. I have thin layer chromatography in the lab with all of those. So I do have all of that. I hate that we're not there, because that's one of the things that I actually wanted you guys to actually see, was that. All right, now with that, um, these are just parts of the spectrophotometer. You have your radiation source, you have a prism that has a slit that is in there, and you have your sample cell, and then you have a detector, and then your computer screen is basically the recorder. Um, so you have those. Now, so when it goes through there, it has when you have the radiation source, what happens is you have the prism and the slit. You put your sample in there, you close the top down on it, and then basically what you do is you have the detector and that recorder all in there. So you have all of that. And then basically, let me go back real quick so I can walk you through it. So they say the prism disperses the radiation into components of wavelengths. So that's what happens first. Then the slit allows only selected wavelengths of frequency to pass through, because you got a frequency detector that if you want to see it at 400 nanometers or 400 wavelengths, um, you can do that and turn it to which way you want to turn it. Then the radiation passes through the sample, and then you have to see which one absorbs at certain frequencies. So that's what you have to see. Then when you do that, the detector measures the absorption of the radiation. So it can be percent absorption or percent transmission. And then that is converted into the electrical signal. And then once it does that, it produces the spectrum. And the absorption spectrum allows the spectrophotometry to be used for the identification. So that's really what happens. Now, most forensic labs uses UV and IR to characterize things. So the two main things that we use in forensic labs, we have in the lab at school, UV vis and IR. The simplicity of UV vis facilitates that it's used as a tool that determines the material probable identity, but it may not prove to be a definitive result. Okay, now the IR, however, is far more complex. Now, you got different materials, they always have different infrared spectra. Each IR spectra is therefore equivalent to what we call a fingerprint of that substance. So that's what it is. So, like I tell all my students, um, each element is different. It offers a different type of fingerprint per se. I tell my students in chemistry, you got elements that fluoresce different. They burn differently. So all of these different spectroscopies tell you that. So you got atomic absorption, how it burns. You got gas chromatograph, how they come out of the column, different retention times. All of that gives you fingerprints and tell you the differences between different chemical substances, between different elements. That is really the truth of what actually happened. Now, here is the ultraviolet spectrum of heroin. This is how it looks. Now, UV-vis is usually around about up to 400 nanometers. So that is how it looks. This is one of an amphetamine, and that's how it looks. So we did this and took it to our lab and actually ran it. That's how it looks. So you have that. Now, when it comes to the mass spectrometer, you have a high beam of electrons that collide with the material that produces positive charge ions. They compose into these fragments, and then those fragments are separated according to their mass. That's what happened. So basically, you shoot electrons into it, and then it just breaks down. So that's really the gist of what's going on. Now, when it comes to mass spectrometry, what happens is that when you have them under controlled conditions, no two substances are going to be the same. None of them. They're not going to be the same. So what you see here is this is a mass spectrum of heroin and of cocaine. This is how they look. If you watch different shows, they use those GC mass specs. You'd have heard people refer to it on like shows like NCIS. I know they refer to it a lot. And this is what you actually see. You actually see something with spectrums like that. And when they identify those particular numbers, sometimes they'll know at what particular numbers what is what. So they know what the mass spectrum of cocaine look like. And then what they'll do is they'll pull the spectrum up of their particular material that they're trying to identify. And then they'll put a comparison of cocaine right next to it or whatever and try to make sure they match up those peaks. And that's how they can identify it. So this is a tabletop mass spectrometer. This is how it looks. Like I said, you got an injection port. It goes through the column. You got your ion source, and then the quadrupole, basically what identifies, and then you got your detector there, and then it goes to your data system, pretty much print out on that computer. Now, let me make sure, okay. Now, the fragment of each component will produce a distinct pattern. And they also, it does it very similar to a fingerprint. So each one is very different. And so that's why I say when they look at it and when they come down to really identifying and really looking at basically what is going on and what type of material it is, what type of drug it is, each substance is going to have its own set of spectra, just like a fingerprint, to identify it. And it's going to show up like that every time. And so this is very important. That's why This equipment is very important. You have a direct connection between the GC column and the mass spectrometer that allows each component to flow into the mass spectrometer as it emerges from the GC. So you can take gas chromatographs, GC, and mass spectrometry and put it together as one instrumentation. And normally, especially in chemistry, especially when we're trying to make new materials and identify new materials, we use this along with FTIR to order to identify and make sure that we have that particular types of substances. So this is what we do. So this is how the GCMS works. So left to right, the sample is separated into its components by the gas chromatograph. Then those components are ionized and identified by characteristic fractalization pattern. And then of the spectrum, and that's produced by the mass spectrometer. So you get all of that and you see all of that on your particular chromatograph. So that's what you get. And that's what comes out. So spectra, chromatograph, all of that comes out into one thing. So you actually see that. You can have them separated into both, but most of the time you can get, one chromatogram that shows you everything. All right. So with that, that is all for this chapter. Um, Hold on just a second. We're going to get started on our next chapter. I'm going to pull it up in just a minute. So let me pull that up. All right. So we just finished the chapter on drugs. And now the last chapter we're going to cover for our next. Is forensic toxicology. So what happens later on? And so let me share this screen with you guys. I'm gonna close the other one out. And let me share. Let me pull that up. And so, ooh, hold on just a second. Let me, uh, Hold on just a second. I was trying to get this set up right and it did something crazy. I just have to pull it back up again. It just did something crazy. All right. Now, it'll work. Okay, you guys, give me just a second. I need to. Do something real quick. So let me just pause for just a second. I just got to make sure this is working, and then I'll be right back with you guys. Okay, class, I'm back. Sorry about that. I had to send a quick email to Dr. Craig. All right, so let's talk about forensics toxicology. Now, we hear that a lot, especially when we're dealing with people who have died in autopsies, because a lot of times that takes a while for it to come back. So I'm going to talk about the first part of this for a few minutes, and then we're going to end for today. And then we will pick this back up on next week. Um, like I said, what I'm going to do is try to get through as many chapters as I can. Um, you guys will probably have probably one or two more tests. I'm going to look at the other chapters, the ones that I cannot get to. What you're going to be able to do is listen to those online. And I'll pre-record those so that you can have the rest of those chapters. So, but we should be able to get through. Today we're on 13. So we will have a test pretty much 10. So we did 10, 11, 12, 13. We'll probably have another test probably after this chapter because I know some of the chapters were short, but we will have some additional tests, probably one or two more. And having those tests on live will be good because that'll help boost grades and all of that for those people who need their grades to be boosted. So that will help out a lot. So let's get into forensic toxicology. So forensic toxicologists, they detect and identify the presence of drugs in your body tissue, your organs, all of that. That is what they look for. I know on a lot of shows, they talk about them being lab techs and all of that stuff, but that is what they do. They really go through and they identify all of that. And sometimes, being a forensic scientist, you do a lot of stuff. And forensic toxicology is just one of the things that you do. They work in crime labs, they work in medical examiner offices. They do reach out sometimes to hospital laboratories and health facilities to identify a drug overdose or monitor the intake of drugs. So they do that. Look at that. Now, one area that is really in particular that a lot of people deal with is alcohol. And they're really big on that because, I mean, just think about it. When you talk about having accidents and all of that that is going on, that happens all the time. Drunk driving and everything. So they look at that. The analysis of alcohol exemplifies primary objective of forensic toxicology, the detection and isolation of drugs in the body, for determining the influence on human behavior. When you're drunk driving, you're impaired. There are a lot of things going on with that. And so just looking at taking a breathalyzer test, that is very important when it comes to those type of things. Alcohol or ethyl alcohol is a colorless liquid normally diluted with water and consumed as a beverage. Now, this is the most heavily abused legal drug in Western countries. 17,000 traffic deaths each year is attributed to intoxication by alcohol. So that is very important. Now, alcohol is a depressant. It primarily affects the central nervous system, particularly the brain. Blood alcohol concentration has been shown to be directly proportional to the concentration of alcohol in the brain. And that makes sense because blood has to go to the brain as well. And so it has direct effect. Now, what happens with alcohol is in the body? You got absorption, distribution, and then you got elimination. Those are the three things. Alcohol appears in the blood within minutes after it's been taken by mouth, and it slowly increases in concentration while it's being absorbed from the stomach and the small intestines into the blood. When the alcohol has been absorbed, a maximum alcohol level is reached in the blood, and the post-absorption or elimination period begins. For an average human drinking on an empty to modestly full stomach, alcohol absorbed into the entire bloodstream takes 30 to 90 minutes after the completion of drinking. Now, when you drink on a full stomach, it takes 2 to 4 hours. So, if you do alcohol, make sure you don't drink alcohol, drink it on what, a full stomach. That's what they're saying. It takes a while. And so, depending on what you got in the stomach, and that's because the alcohol is absorbed into the lining of the stomach. Even though it's acid there, and I know I have students that come to me and say, well, it's acid in the stomach, it'll dilute it. No, those are all types of different chemical reactions going on right there. And it doesn't necessarily dilute it. It can exacerbate things too. So that is what happens. So when people get sick, people get major hangovers and all of that stuff, a lot of times it's because they don't have enough food on their stomach. That's what it is. The type of beverage also affects the absorption time. For example, beer is absorbed more slowly than 80 proof alcohol because of the carbohydrates in the beer. Because beer has carbohydrates, it affects the absorption time. The longer the time for the completion of the absorption to occur, the longer will be the peak alcohol in the blood level for the given number of drinks. So, when absorption is complete, alcohol becomes uniformly distributed between all watery portions of the body. And that's about 2/3 of the body volume. So, if blood is not available, other watery portions of the body, the brain, the cerebrospinal fluid, and vitreous humor, can be used to determine the alcohol level. So the alcohol goes all throughout the body, and we're made of mostly of water. That's where alcohol is going to go because of the chemical composition of alcohol. It's ethanol, ethyl alcohol. What's the difference between ethyl alcohol and water? Is an OH group, and I'll talk about that in a minute. So how do you eliminate it? Oxidation and excretion. Oxidation takes place mostly in the liver. The enzyme alcohol dehydrogenase converts alcohol to acetic acid and then into carbon dioxide and water. So that is what happens in the liver. So in our bodies, we have an enzyme that is called alcohol dehydrogenase, and it converts the alcohol to acetic acid and then into carbon dioxide and water. So it goes through all of that. Now, 5% of alcohol is excreted unchanged in the breath, urine, and perspiration. Blood alcohol is concentration is defined as the percent weight per volume. Hence, 0.1% of 0.10% is equivalent to 0.10 grams per 100 milliliters of blood. That's how they determine your blood alcohol level. Now, because it's excreted unchanged in the breath, that's why they use breathalyzers. When they look at certain drugs, that's why they use urine, perspiration, and usually they get that off of hair too. But more so, they use breath and urine for alcohol. More so, breath than anything. The elimination or burnoff rate for alcohol varies, and it's 0.015% per hour. That's about the average. If your blood level alcohol is 0.10%, it takes it about 6 hours for you to come down to zero. So for the alcohol to get out of your system, depending on how much alcohol you have, it can take a while. it really can take a while. Now, you can have blood alcohol concentration, BAC. Uh, so how they do that, they measure the alcohol content in your breath. That's why people have breathalyzers. They have gotten so strict and stringent these days that, people that have several DUIs, they have to take breathalyzer with them. They can't even get in their car until they take a breathalyzer test. Their car won't crank until they take the breathalyzer test. That's what they're doing now. They are being really strict with this because of how many automobile accidents and everything that's happening. And a lot of people, especially if they've been driving under the influence, can go to jail for manslaughter or vehicular homicide because of driving under the influence. So this is what they said. Basically, the evidence verified that the amount of alcohol exhaled in the breath is directly proportional to blood concentration, and that is directly proportional to alcohol in the brain. So all of it is directly related. So that's why you can take a breathalyzer, because it's already been determined that, hey, all of this related. It goes to the brain, this is what happens. They have been doing research on this for years because people still get in the car, people still die by DUIs while somebody's driving under the influence. The current legal measure of drunk driving in the United States is 0.08% or 0.08 alcohol per 100 milliliters of blood. Is 80 milligrams per DL. So that's what it is. So 0.08. That is what it is in the United States. In some areas, they make it even lower than that, depending on your jurisdiction. But that's the consensus around the United States. Now, alcohol, what happens is absorbed from the stomach and the small intestines, and it is absorbed into the bloodstream. Because ethyl alcohol, normal body temperature is about 96 to about 98 degrees. Ethyl alcohol can absorb through the skin, or absorb because of the high temperature of the body. And so because of that, because the temperature is so high, it can just absorb really quickly, because the boiling point of ethyl alcohol is really no more than about 75, 80 degrees. So it can go into there pretty quickly. That's what happens. Now, alcohol is carried to the liver where the process of its destruction starts. Blood carrying alcohol moves to the heart and it is pumped into the lungs. Yes, it messes with your circulatory system. Humans have a closed circulatory system. You got hearts, your arteries, your veins, and your capillaries. So alcohol can do a lot of destruction when it comes to the body. And so this is just an example of the circulatory system. You got your lungs, your pulmonary artery, your veins, your body tissues, all of that. In the lungs, the respiratory system bridges the circulatory system. You have a rapid exchange that takes place. Fresh air in the lungs, alveoli sacs, and spin blood in the capillaries surround the sac. If alcohol is in the blood, it's going to participate in that exchange. That is exactly what's going to happen. And as one exhales, the carbon dioxide and the alcohol leave the blood, and the oxygen enter the blood in the air sacs, known as the alveoli. The alveoli sacs that the alcohol is in is going to become in equilibrium with the blood. That's what's going to happen. And then after leaving the lungs, the oxygenated blood returns to the heart, where it's pumped to all of the body through the arteries, the heart, through the blood veins, and that completes the circulatory process. So if you take alcohol, it's all in everything. And then you have your gas exchange in the lungs. Um, that is what happens. So the blood flows from the pulmonary artery into the vessels. That lie closest to the wall of the alveolar sacs. Here the blood gives up its carbon dioxide and absorbs oxygen. The oxygenated blood leaves the lungs via the pulmonary vein and returns to the heart. Yeah, so now when we deal with that, you also have to deal with the respiratory system. The trachea connects the nose and the mouth to the bronchial tubes. The bronchial tubes divide into numerous branches that terminate in the alveoli sacs in the lungs. So y'all going like, what does it do? It slows down everything. That's what it does. The normal temperature when the breath leaves the mouth is normally around, when they have done all of this, 34 degrees Celsius. So really normal body temperature. Now, the breath testers operate on the fact that at 34 degrees Celsius, the ratio of alcohol in the blood to blood alcohol in the alveoli breath is approximately 2100 to 1. I know y'all gonna like, what does that mean? In other words, 1 millimeter of blood carries the same amount of alcohol as 2100 millimeters of alveolar breath. Breath testers operate on this principle of infrared light absorption becoming increasingly popular within the law enforcement community. That's what they use. Many types of breath testers are out there to analyze, and what happened is it's exposed to infrared. So that's why they can get it back so quickly and they can do it right there. What is going on is basically the interaction with the infrared. Now, they also use some breath testing devices that use fuel cells as well, converts the alcohol to an electrical current. So they can even make this to where it's handheld and they can test this. That's what they can do. Let's see. I am gonna stop here. This is just an infrared breathalyzer machine. This is just how one of them look. Right here, like I said, they got handheld ones that they use now. Um, and that's what they do. They take it and they have a subject blow into the actual tester itself. And that's what it is. It got an infrared radiation source, breath in, breath out. It flows into the chamber. There's a filter, there's a detector, and it tells you how much is in there. That's what it does. And so that's what it does. Is infrared light beams through the chamber. Alcohol in breath absorbs some of that infrared light. The filter selects the wavelength of the IR light with in which the alcohol absorbs through there. The detector converts it into electrical signal, and the content is converted into a blood alcohol concentration, and it's displayed on the readout. That's pretty much what happens. Now, I am going to stop here because this gets into the field testing. So they use sobriety tests and everything. So we're going to stop here um, for now. Um, like I said, I'm going to look and see. We'll be able to get through a few more of these chapters. Um, so you'll be able to have a few more exams for those of you that want to push that grade up a little bit. The more exams you have, uh, the less weight they are, but they will up your grade a lot. So what I want you guys to do is really study. Um, we'll finish this up on Monday and probably have a test on next Wednesday. Um, yeah, we'll probably have a test on next Wednesday. Um, and then I'll do a few more chapters. What I want to do is try to get 2 chapters. We on 13 now. I really want to get to chapter number 15 or 16. Well, chapter number 17 really, and then 18, 19, and 20. I can put up. We may not test on them because I'll just pre-record those. But what I'll do is pre-record those last few chapters, and then you guys can have some extra exams. What I will do as well is put up a really big study guide for you guys, so that you guys can have those. And like I said, I just haven't gotten to it yet. I will give you guys a few more discussion questions that you guys can answer also to help up your grades if you need a boost in your grade. So I'll make sure you guys do that. Um, and I will make sure I also open up all of the concept maps for all the chapters. You guys will have a comprehensive test. I will put up a study guide of what questions and everything that will be on the test. So I'll make sure that I get that done and put together for you guys and try to get it up this weekend so you guys can have time to study for your finals and everything. So we're gonna probably have about 2 more exams. Like I said, I'm just trying to help boost your grades if you need a boost in your grade and everything. So we'll cover all of the chapters in the book. So we'll probably do the rest of 13 on Monday. We'll have a test probably that Wednesday. And then we got literally basically 2 more weeks. So I'll probably go ahead and try to do chapters 14, 15, 16, and then the rest of the chapters I'll go ahead and pre-record. So you'll probably have a test on the 15th and probably have your last exam on the 29th. So you'll probably have 2 more exams, and you'll have your last one on the 29th, and I'll go ahead and start prepping for you guys final. If you got any other questions or anything, send me an email. I'll try to get everything up for you guys and get everything done. That's all that I have for now. Like I said, if you got any questions, let me know. And I'll get back to you guys and talk to you guys more on Monday. Have a good weekend. Like I said, if you need me, reach me via email, send me a note on Canvas. Perfectly fine. All right, you guys, have a good one. I'll talk to you guys later.